Hello everyone, my name is Maciej. I currently work in Berlin in Germany, but originally I'm from Poland. So when I came here, I love learning languages, and when I came here, my first thought was, great, I read Ukrainian a bit, I can probably speak it, and then people were just looking at me politely, and that wasn't a good thing to start. So, okay, this talk is in English, question and answers will be in English, but later on, if you want, we can try this Polish-Ukrainian mix. Maybe it will work. I don't know. Okay, so Wire. Wire is my company. It's a secure end-to-end encrypted messenger. From all secure messengers, Wire is the most beautiful. From all the beautiful messengers, Wire is the most secure. This quote is unfortunately not mine. My colleague Artyom made it, and I'm very jealous of him. Also, I'm very freaking out when everyone is looking at me. So please just enjoy the video and don't mind the guy behind the desk. So. Yeah, Wire has to work on a multitude of platforms. We want everyone to be able to communicate. So we have many languages. I'm working in the Android team, and in Android we work in Scala. There are also a team working on iOS, on the Windows, on our web platform. They are using other things. And there's also the backend, which is written it's like a completely different beast. It's written mainly in Haskell, which may be of interest to you. And the cryptographic part of it is written in Rust. Some time ago, we thought that coding a mobile application should be quite similar no matter the platform. There were different ways of writing UI, but by definition, the UI should look almost the same in each case. And the logic behind it was the same. So we thought that this logic part can be written once and used everywhere. It was called Sync Engine, it's like a synchronization point between the teams. And the first attempt was to write it in C++. It wasn't the best idea. The life cycles on mobile applications are very different in iOS and Android. A life cycle is like a sequence of events that is happening to each application. The application can be created, then it can be, some fragments of it can be created and displayed on the screen, then it can be paused, restored, it can be also, after all, destroyed, as everything in life. So in practice, we found out that the whole code was polluted with if-else statements everywhere. If we're under iOS, do this. If we are under Android, don't do that, and so on. And eventually, a decision was made to split up the code completely. And so we had one sync engine for Android, one sync engine for iOS. And since they were now dedicated to their platforms, we were able to rewrite them in technologies that are like better suited for the given platform. Maybe there is some sort of a like far-fetched analogy to my experience here that we shouldn't really just use one language that we like and expect everyone to understand that we should use just something that really fits the platform. Okay. So in case of the Android, even if it's written in Scala, if it's written in Java, Scala was proposed and accepted. And one of the reasons, if not the main reason why it was accepted, was that Scala is beautifully reactive. Yay. A messenger is supposed to transport information instantly across the network. It reacts to the user's actions, composes messages consisting of text, pictures, like some animated GIFs, audio and video recordings. And in our case, because we are like a secure messenger, we encrypt it and send it to the server to another user. So we don't know what's there in the message. We just send it to other people and they have to decrypt it. But also, we have to inform the user about a new message or a call, and we have to also react to Android itself, because we also have this communication with our operating system. From the application point of view, Android quite often acts as a law enforcement, and it sends us some requests, and we can't ignore them. We have to do what it says. We have to react, for example, stop the application and perform some task, but we have to do it in a civilized way. All data has to be safely written down, resources have to be released, and so on. In other words, we have to be reactive. So the way we code things is very tightly connected with what vocabulary do we use, at least in my experience, in what vocabulary would we use when we explain how these things work. If I start to use the word reactive to describe certain behaviors, in short time I will use this word like more and more. So let's extrapolate. If we can talk about the application reacting to external events, then we can also talk about the parts of the application reacting to things happening in other parts of the same application. So let's say the user goes to the settings and changes the preferred color. Our application can then react to that user action by changing the colors of buttons and the backgrounds. Or let's say we have a controller that is listening to what's happening in our storage, and when something changes in that storage, then the controller updates some part of the view accordingly, so something changes in the display. Or if the user switches to another conversation and there was a video playing in the old conversation and there's a video controller, then it's not just changing the conversation that stops the video, but that controller knows that we've changed the conversation, and then it sends a request, okay, stop that video. Okay, how do we implement that? In Android, and generally in Java, we have callbacks, and callbacks are for everything, at least in the old way. Let's say there's a simple feature, a grid with emojis, which can be added to the text of the message. You can usually see there's a keyboard, and when you click on an icon on the keyboard, it changes with a list of emojis. You click on an emoji and so on. So when the user wants to add an emoji to the message, we have an interface for that with a method called onEmojiSelected, for example, and our conversation fragment implements that interface. Then there's an adapter. I'm talking a bit too fast for this video. Okay, we have an adapter, and it contains a click listener. And when the user clicks on an emoji, the listener calls that onEmojiSelected method in our conversation fragment, and then the emoji is inserted in the text. So, okay, that's quite complicated, I think. And imagine that instead we can easily implement a way for the emoji grid to just broadcast the emoji, the information, what was clicked. And our text field can react by itself to that broadcast and add the emoji to the message. This device for publishing and receiving information is called an event stream. And an event stream is let's say it's an implementation of the observer pattern. It is possible to do it in Java, of course, but in Scala it's much simpler. Instead of an interface implemented by our publisher, we have an instance of a concrete class, much smaller. We make it into a field of the publisher, and every time a change happens, we inform our event stream instance about it. On the other end, we subscribe simply by providing the event stream with a functions body. That's it. So here we have this onEmojiSelected method, and that part at the bottom is really just like an argument to that method. But because of the syntax sugar in Scala, we can write it this way. So yeah, this way, in just a few lines of text and few lines of code, we do what in old Java way with callbacks would mean a few classes and so on. So I'm not saying callbacks are maybe were good some time ago, but now they're certainly too complicated. By the way, if you know ReactiveX or another library using event streams, then yeah, it's all very similar. So what I want you to remember from this talk is that I'm not talking only about our implementations. I'm not telling you that okay, let's just use what we have, because our way of writing this event streams is very tightly connected to how our code works in Wire. But I would like you to get interested in the whole concept of event streams. So there's ReactiveX, also ReactiveX for Scala, and there's, for example, the ScalaRx, very similarly named library written by Lee Haoi. He's a great guy. He does really a mountain of good for the Scala community, and he also created something similar to what we have in Wire. The main difference, I think, is that in ReactiveX, event streams are very powerful. And in Wire, instead, our are very light, very minimalistic. And they are faster. We can map them and filter them, but there's, for example, no flat map. And if the event stream was created somewhere in the past and already started propagating events, and we subscribe to it only after some time, we're not able to learn anything about the previous events. We can only wait for a new one. The reason is an event stream does not have an internal state. It only propagates packets of data, so a flat map is not possible. For that, in Wire, we have another tool, like a event stream on steroids. It's inspired by a similar feature in Haskell, and it's called a signal. We can think of a signal as a smart variable, a variable whose value depends on the state of another element in the application. When the state of that external element changes, the value of our signal right here changes as well. We can either react to those changes, and then it works more or less like in the case of an event stream, or we can simply access the current value of the signal when we need it. Think traffic lights, for example. We see the current color and act upon it, but we can also react to the change of that color. So in Wire, we use signal everywhere in the Android version of the Think Engine. It makes the whole thing quite more clear. We can really think about it in a more abstract way than we did when it was in C++. Yeah, and if you want, you can also take a look at how we did it. Everything is publicly. You can just go to GitHub and see it. Yep. So yeah, that's a very nice icon too. Why I added it? Okay. So now I would like to talk for a few minutes about some real-life example. So what happens when you open Wire and send a message to another person? For the simplicity's sake, I would like to avoid corner cases, and I will lie, well, maybe not lie, but oversimplify in a few places. But apart from that, all that code we will talk about, you can find it on GitHub and see for yourself. So, of course, every application can be seen as some sort of a onion with layers upon layers. The outer layer in Wire is, of course, user interface. It's the Android widgets and the views and everything that is displayed on the screen, and also what contacts the Android itself. Some of these views are still using listeners, especially because Android is written in Java, but we gradually migrate them to signals. Just beneath, we have controllers which connect the user interface with the Think Engine. But even within the Think Engine, we have layers. Two big ones are services and the backend API, so to say. The gap between them is filled with the storage. The storage is like this pumping heart of the whole application. It's where most of event streams and signals originate. Whatever moves in either direction has to be saved, and the other side reacts to the update of a respective signal or event stream. This way, we can be pretty sure that no matter what happens, the application is killed by Android, the phone dies, there's an application crash, Android wants us to do something, the data we send and receive is safe. So it's quite a functional way to handle mutability. We do things because we have new versions of the old values, but we don't just assign them to variables. And so if you want to do it this way, if you want to simply implement a storage and add some signals and event streams, then this is really the core of a working mobile application. Okay, we will start with the text field used to type the message. The text field is a widget, so we have to use a listener because this is how we contact the Android operating system. In this listener, we implement a method which is called by Android every time the text in the text field changes. We use that to publish the changes, and the moment it is published to a signal, so no more listeners. The view containing the text field is connected to the controller. One of the fields of the controller is the signal, entered text. This is where we publish our new text. And our first interaction with the person we want to send the message to is a typing indicator. Just as we start typing, the application sends a notification that we're typing something. That's like, haha, that's very important part of the application, of course. It's a very simple packet of data, so it's a good opportunity for us to discuss how information travels in wire and in every messenger, really. First of all, the controller has to know who are we talking to. In wire, apart from the very initial state, just after the installation, one of the conversations will always be the current one. There's a signal which holds that current conversation ID. You can simply access it. So here you see for comprehension, and this is a for comprehensions on signals. So there's more robust versions of event streams. This way, every line of this for comprehension is in fact a flat map. So we're flat mapping the first line to the second, to the third, and only then we do something with the result. And in every line, we say that we want to get either the current value of that signal we want, or that we want to wait for the value when it appears if the signal is empty at this moment. So we can, this way, only in a few lines of code, we can make this thread of the application just to wait for some changes. And by these lines of code, we say that every time the entered text is changed, we want to access our current account, then get the current conversation ID, then access the service, which implements how the typing notifications are handled, and then inform the service that we wrote something. Every time we update the entered text or switch the account or the current conversation, the controller will react by calling this method. Please also note the order. We can safely assume that the account changes not as often as the conversation, and that is still not as often as the text update. Otherwise, if, for example, we put the entered text at the top, with each text update, we would also, it will go down, and we will also query the account and the conversation, even though they usually do not change. So, okay. The user typed the first letter, and the controller reacted to it by calling a method on the service in the sync engine. The service creates a request and puts it in the storage. Yep. And that's the storage. And this triggers an update in a signal held by the backend API on the other side. On the other side of the storage. A storage, don't mean only the database. In fact, we don't put a typing request in a database. We only put it in some kind of a only memory part of the storage. But we use it as one. If you look at, I show it here as one abstraction. Okay, the sender gets the ID of the conversation and transform our request into a post request, and that conversation ID as a post request goes to the backend. The backend is in charge of identifying the receiver of our message and sending it there, either as a Firebase cloud message, it's a library used by Google, or through a WebSocket. It's either or. We in Android, we trust our colleagues from the backend that one message will come to us only from one of these sources. However, we consider FCM, the Firebase cloud messages, to be unreliable. Messages sent to FCM have a nasty talent to go missing. And if you use Android, you probably experienced it. WebSocket is more reliable, but it's heavy and it drains battery. So if WebSocket is on, we can assume we receive all the messages and can simply process them. But if we receive an FCM message instead, we can't be so sure. In fact, we use it only as an indicator that someone wants to contact us. But we ignore the contents of such message. Instead, we perform a fetch. That is, we send a request to the backend asking for all the messages it has for us. Okay, so we're now on the receiver side. We have our timing message. We deserialize it. And please note that the backend does not know which conversation is the receiver's current one. It knows it only about the sender. So it will feed the receiver with all the typing events happening in all conversations, which the backend knows that the receiver is interested in. The receiver listens to them all, groups them by conversation, which is and stores them, and on the other side of the storage, they are published in an event stream. But an event stream does not have an internal state. We can just access it and ask, hey, is someone typing in this or that conversation? This is not how it works, which is good because we want only to know about one conversation. We can ignore all the others. So back in the controller layer, this below that line, we have something like this code. Again, we have a sequence of signals. One is evaluated every time we switch the account, the other when we switch the current conversation, and the third when the list of typing events in the conversation changes. So that last line creates a signal on top of the event stream. This typing users map non-empty. We can simply map a signal to another signal, and this new signal is simply Boolean, true or false. And then back in the view, we can listen to that signal to show an animation on in our view, in our display. For example, in this case, it is a pencil writing my name because the signal is true, so we know that me from the sender side, I write something. Okay, so let's go back to our text field. Before we start typing, we don't even see the send button. Wire likes a certain minimalism, as in don't pollute the user interface with all possible action buttons at once. So in place of a send button, initially we see a small hourglass. Clicking on it will let us set the timer after which the message will disappear. But the moment we start to type, the hourglass is gone, and the send button appears instead. Both the hourglass and the send button are controlled by signals which are mapped from the entered text signal in the controller. The moment the value of entered text becomes empty, the hourglass appears. The moment we type something, entered text changes, and the send button appears, and the hourglass is gone. OK, so let's use it. Let's type this hello world and click that done button already. OK. Two things happen here. First, we send a message. We access the signal with the current conversation ID. Then we access a service for sending messages. And finally, we call the send message method on it. That's the send message. And when this is done, so when we actually send the message, then we publish that fact to the event stream. It is then listened from the other place in Wire. For example, the text we send also appears in our own conversation. We also want to know what we wrote before. The call to the send message method actually sends a message. The path is similar to the typing indicator request, but this time we really store something in the storage, in the database. And the service creates a request, saves it. The request is then picked from the storage by the sender on the other side, transformed into a post request. And one more thing is happening, encryption. And on the receiver side, the message is decrypted, the backend, so the backend does not know what the message is really. And then after being decrypted, it is put in the storage. But encryption is like a completely different issue, very big. We would need another presentation for that. OK, so the post request, apart from the message content, has also some metadata. Among the metadata, we have the ID of the conversation and the timestamp. When on the receiver side, with the message is written down to the storage, it is within the context of the given conversation, and it is ordered by the timestamp. On the service side of the storage, we have a message cursor, which is an abstraction over the database service side of storage. So it's like we can see a window that is moving in the database, showing us only a part of the messages that we are interested in the given moment. When in the receiver the message is written down to the storage, it is in the context. And in the UI, we have a separate view for each message. But since there are so many messages, and most of them are not visible in any given point of time, we don't want to create and destroy these views. We want to reuse them. It's a very common concept in Android. It's called view holder. Yeah, it's a pattern used everywhere. So we have this visibility window, and it's reacting to the events such as the user switching to another conversation or scrolling up or down. That wrapper interacts with the Android recycler view, and that displays that message, that information, hello world. All And there's one more tiny detail. In the same time we send a message to another user, we display it in our own conversation. And it can be in one of four states. First, we display it with a footnote sending, indicating that the message is in the process of being sent. When the message is sent, we receive a confirmation or an error. If it's a confirmation, we add a small note sent. If we receive an error, we display the error message in the same place. If the message is received by the other guy and then displayed, then the fact that it is displayed is also, it triggers a receipt. Just as the typing indicator, a receipt is a small message without any actual content other than the information that the original message was displayed. It goes like all the way back through the backend to the original sender. And finally, the view on the sender side gets notified. Yeah, so it goes through the backend to the storage again. Then we have this received event. Yeah, and from the storage, even though it's not, it's not really stored in the database, only in memory. Then it goes through the controller back to the view, and then we have this footnote changed to delivered. So mind you, all this is only about sending one text message in one-to-one conversation. And if I can only show you now for a moment. So this is this whole diagram for sending one message and one typing indicator and one receipt. And so you can see, even though we try to be really consistent, we try to use the best patterns we can, it's still a mess. Like, your application grows and you have to deal with it somehow. But anyway, if this was not, if there were no event streams, it would be much, much more messy. All right, let's go back here. So there's this idea that on the presentation, on every talk, we should always say the most important things in the beginning or in the end, because in the middle, everyone is looking at their phones anyway. So I told you about my work at the beginning. Now I would like to tell you if one thing I would like to remember from this talk is that, let's start again at some interesting point. Okay. It's that a good technology is a technology which lets us keep things simple. The human mind may hold only so much complexity. If our application is already complex on the low level, we will struggle when it comes to adding to it more high-level features. We will not be able to remember all the details. We will forget about corner cases, and it will take us more and more time to work with the code. There are two ways to remedy that. First, keep away from abstractions if they're not actually useful, but only they look smart. Of course, it may happen that in the future these abstractions will become useful. And that's why it's nice to have a language which makes it easy to refactor the code. And Scala is, I think, awesome in that respect. We have a lot of ways to hide the code that is ugly, or that we just don't want to, we just want to have a specific ways to interact with the outside world. Second, if we are able to encapsulate that complex logic really well, possibly with use of syntax sugar and special features of our language, like in Scala, then we can actually forget what's inside. We can throw away it from our minds, making room for more high-level stuff, making our application more robust and more epic. So yeah, thank you. Some of the icons I used were made by artists who cooperate with FlatIcon. The sketch of a meme with aliens is made by Half Hefner. This video was made with VideoScribe. Ta-da. And my name is Maciej. Thank you for your time.
Some questions? when writing Android applications with Scala, there's always this issue that Android phone has all the libraries for Java and I guess Kotlin installed already, and Scala libraries are like a big thing and you use a lot of the valuable space on the phone. How did you address this issue, or how did you encounter it?
Well, maybe I can use just this. Okay, so Wire is not a small application. It takes, I don't know, it probably depends on the version, up a few tens of megabytes. We use the Android DEX files in a way that when your number of methods in the program is small enough, they can be put in only one DEX file. So it makes the application like small enough to some level. And then when you go like make your application only a bit bigger and you go outside this threshold, then the application suddenly grows. So we try still to keep this one DEX file. But yeah, yes, Scala makes us use new things, add new libraries to the application, so it's not really a very light one. But still, it's quite fast. And so this is only the size of the program, not the size of the, like, it's not heavy so much.
I have two questions. First is about you tried to use Scala also for other platforms than Android, and it didn't work, right? So you had to switch to
no
specific languages. No.
No. At the beginning, the idea was to write the logic part in C++ and to have this one common logic part, the sync engine for every platform. So it would be then compiled on iOS, compiled for Android somehow, compiled for the web version, and so on. But that didn't work. So we split the code completely. Only like the abstraction level, the design were the same. Generally, I like it very much that the company is always going first with the design and only then with we're trying to implement the design that is common to all platforms. But we write Scala only in Android. In iOS, it's Swift and C#, I'm sorry, Objective-C. And in web, we use Electron, so JavaScript.
I see, okay. And the second question is about Rust. How do you actually integrate Scala with Rust encryption for encryption? And
Rust is used on backend side because no, yeah, okay.
So Scala is also on the
Scala,
backend side?
No, on the backend we have Haskell with Rust. On in Android we use Scala, and we got this libraries already, written in Rust and then compiled for our platform, and we have some kind of API to connect them. But the cryptographic part has to be really quick, so we simply it's the same with the video. Really, we also have another part that is written, I don't know in what, C++, that governs the audio and video calls. So we call them with Scala, and they simply then give us some results in futures.
Okay, and the API you mentioned, which you call in Rust, it's called from Scala. So you call somehow Scala, Rust from Scala. Is it?
The same way like we would call C. Rust can be simply compiled to the same bytecode. So I'm not an expert in that, but from what I see, it's not very different.
Okay, thank you.
Android SDK has a limitation on amount of methods. It's a few thousands, and Scala SDK almost feel this limitation. It was this problem was emerging of Kotlin for solving this issue. Did you face with this problem?
The problem of having too many messages?
Yeah.
Actually, it's the other way around. With Scala, it's very easy to, comparatively easy, to make, to like think with one method processing, completely independent from like the whole bunch of other messages. So we have only like a few places where we really have to consider that there can be some kind of a flood of messages, and we have to deal with that. But in most of our code, we have it very concurrent, and we only deal with the one or a few messages at once.
Thank you. My second question, Scala is a really heavy language, and does Scala is suitable for invoking the code over ARM virtual machine, special for Android?
Yeah, we are close to the limit. That's true, but yeah, with Scala, with this level of abstractions, we are able to, let's say, to really control how much data we use. It's like you know, the fastest method, the method which uses the least amount of memory, is the method that is not called at all. So with event streams, everything is basically lazy and just waits for something that needs to be done, and we can focus on making it work only when it's really necessary. So we can avoid situations when we call methods and then the results of that methods are not used. So yeah, I think really Scala is a very nice language for Android. I would like it to be used more.
Thank you.
Okay, thank you.
That's all. Thank you.